So, last step we did was to say, okay, we want to truncate. Truncating by standard deviations were not necessarily the smartest idea. Let's truncate by quantiles. Empirical quantiles, it's not good. Let's so we need to somehow maybe privately estimate the quantiles. But once we discuss that, we actually go back to an idea that you raised at the beginning of the lecture. Well, maybe we will do private estimation of the median and not of the mean, and that will be more helpful and more easy, because median, we know, is a more robust estimator, more robust statistic. Right? Like mean can arbitrarily change by changing one extreme element. Median, most cases, doesn't change nearly at all. So
most cases.
Exactly. So now we need to think whether median is easier to privatize than mean or not. Now, why should we do it? For two reasons. One, in some cases we care about the median, right? Like, even had I found a very good technique that will privatize the mean well, that's only one value out of the entire process. I would want to do a bit more, so I would want to ask what the median is. But also in many distributions, median and mean are not that far apart from each other. So, again, in the scale of the range, they're much, much closer. Right? Like, we're now in the problem where we don't know if the average salary is around 5,000 a year or around 200,000. Like, theoretically, we have no idea what's going on. So that is the scale of the uncertainty. And typically, even in crazy distributions, the median and the mean are closer to each other way more than the scale of the range. Like, the distance between the median and the mean is much smaller than the full range. So it should be helpful to some extent. Okay, so the median indeed is a very robust statistic. Right? I can change a single element and change the mean by more than the median in the typical case. But in fact, I can construct the same way I constructed the data set where the 99th percentile move. I can also construct a data set where the 15th percentile moves. What is the sensitivity of the median to a change of a single element?
It's pretty big. Let's see, around...
Not this example, in general.
It can be the whole range.
It's the whole range. The mean at least had the range divided by the number of elements. The median doesn't even have that. If you have exactly half and half are minimum value, half are maximum value, and you change one element, so you move the median from the minimum to the maximum, or the middle to the maximum, depending if it's even or odd number of elements. So even though it's more robust in the typical case, in the context of privacy, it's even more sensitive. And why is that? Because what we care about in statistics incorporates a lot of the statistical aspects, a lot of the distributional aspects of the thing you want to quantify. Everything is defined with respect to a distribution, where privacy is worst case. So when we do statistics in a private manner, we're playing this weird game. The way I tend to think of it is like there are two people I need to keep happy: the privacy person and the statistician. And each one of them has his own weird idea of what's okay and what's not. Each one of them is worried about other things. And my goal in coming up with a new sophisticated algorithm is to find this middle ground where, like, I incorporate assumptions, but only in a certain point. So, like, this dude, the privacy dude, is like, any distributional assumptions, I can't trust them, whatever, but the statistician is okay with. So I'm like, okay, so I'll do this operation where, from privacy perspective, I will say, regardless of the underlying distribution, regardless of the data set, I would always protect you. But to the statistician, I'll be able to say, well, but this operation won't cause harm in typical cases, in typical distributions, so you should be happy. And like, this is basically what a big portion of what privacy research looks like these days is like finding definitions and sensitivity measures and mechanisms and perspectives that sort of manage to thread the needle. Have some process where the sensitivity is bounded in worst case, but the damage to utility is negligible in typical case, or something of that sort.
So in pathological cases, well, say that it's pathological and there's nothing to do with it.
Wait,
Or
but
nothing.
from privacy perspective, you need to say what you do there, and you need to reason about that thing that you did. Even if your algorithm says, I will somehow identify that this is a pathological case, and let's say refuse to reply, or then put out a random number, or whatever, you still need to reason about the privacy of identifying this to be a pathological case. But once you did that, you're in good shape.
And the statistician, if it's pathological, throw it to the trash.
Exactly. So this is so we already started doing that, right? So clipping and things like that is basically we said, oh, if it's going to be like a crazy weird data set, then we might have like a significant effect in the way we're clipping, but that's unlikely, and then you're okay. Now we didn't reach something amazing, right? Like this is the best we got. So far, which was like not very wrong, but was clearly biased. So statistician is not excited, but won't be furious. But we can hope for better stuff. Okay, so now with the median, we're in really deep trouble because the privacy dude is like really annoying. He's like, yeah, but there is a data set with half zeros and half 10 millions. But like, yeah, but that's typically not my data set. But okay, how can we satisfy? So here comes a new trick. And this is another thing that was developed in the privacy community, but in a sense has many use cases even in statistics. And that is, one saying, if you can't get what you want, so want what you get, or something like that. So this is sort of what we're doing here. It's like, okay, the sensitivity of the query of changing a single element is really bad. So maybe I'll change my query. So when I say the sensitivity is high, what do I mean the sensitivity is high? The median changes by much. What's by much? What is the unit? The unit is the unit of the quantity I'm estimating, dollars in this case, or centimeters, or whatever is the unit of measure. Median has a different natural error measure, and that is the rank. If I give you a distribution, which, so basically for every value, in dollars, in this case, I can tell you what is its location in the, had I added this element, where would it be in the sorted data set? Okay? And the median is a value that its place would be exactly n over 2. I mean, again, up to maybe rounding or whatever, if it's even or odd, but okay. For simplicity, let's assume that any value between the 500 and the 501 is okay. So if I give you a number that's between, that had I plug it into the data set, would be located in 503 location, or 597. Again, I'm using a 1,000 size data set, for example. You would probably say that this is a good response, not perfect, but relatively reasonable, and you won't ask, but how far it is in centimeters and dollars. It's like, yeah, I'm looking for the median, and it's nearly the median. Okay. So that tells us that a natural option would be to to think of a different utility rather than the distance in absolute value or square distance from the correct value, the distance in rank. What is the sensitivity of the rank measure to a change in a single element? That is, if I take a value and I ask what is its rank in some data set, and then I change one element in the data set, how much did the rank change? Wait, that's one. Well, that's cool. My sensitivity is all of a sudden bounded. Bounded by...
Yeah, bounded in your new definition.
As I said,
much.
If you can't get what you want what you get. So yes, I changed my accuracy definition, but within that accuracy definition, my life is perfect. Now, okay, will the statistician be okay with it? The truth is that they should be. Why? Because if your distribution is such that moving a few elements in the data set, few ranks in the data set, will change significantly the value, then your generalization error, the sampling error, will also be large, because it means that the distribution is very unstable. If you are in a stable distribution, then you already assume that there is a high density around the median, and if there's a high density around the median, it means that changing the rank by a little won't change the distance by much. So the statistician should be happy as well. But for now, let's start with the privacy. So okay, this is what I will get in. If I just add noise that scales with the range, this is like you don't even notice, but this is the same plot as before. It's just that the difference in the scale between the two noise additions is like crazy. And here's the inverse sensitivity idea. So here's some data set that I chose, and here is the loss in rank for each value. So the true median is here, 20 something, and in thousands of thousands, 20 something thousand. And what you see here is for every value, how many places away from the median it is. And as you see, there's a very deep well. Why? Because there is a very the data set is relatively concentrated around that point. So what can I do with this? I can sample proportionally to, or inverse proportionally to that loss. Exponentially inverse proportionally. This is the exponential mechanism. What does the exponential mechanism tell us? It tells us that if we have any loss or any score, right? Score is when positive is larger is good, and loss is when larger is bad. If we have any score or loss that has bounded sensitivity, then we can sample exponentially from the pool of all possible outputs with probability that is about proportional to e to the minus the score over 2 epsilon. And this is private. Right? Because changing one element will change the score by whatever is the sensitivity. Sorry, 2 epsilon times the sensitivity, of course. I'm assuming sensitivity 1. And that 2 is 1 for the numerator and 1 for the denominator. So we're good. Yeah, but the exponential mechanism is inefficient. So that on its own is not a good solution. So here comes the cool idea. So the inverse sensitivity mechanism is, generally speaking, one of the most natural applications of the exponential mechanism. So there's the exponential mechanism, the inverse sensitivity, and then inverse sensitivity for median. Exponential mechanism, sampling proportional to the score. inverse sensitivity, defining the score as how many elements I need to change in order for this value to be the correct empirical value, which is always sensitivity 1, so that simplifies things. But still that might be inefficient because I need to compute for each value, all the options. But when it comes to a data set in the median, it's really convenient. It's basically sampling exponentially how many steps away, how many elements away I need to move, and then uniformly sampling within that interval. So it's a bit more complex. I won't get into it here, but generally speaking, the idea is it's inverse exponentially to how many steps away with something that has to do with the width of the intervals, which is why we still need a range, because we need the two intervals that are less than the minimal empirical value and more than the maximal one, but our dependence on that range is only logarithmic, not linear. So for all intents and purposes, it basically doesn't have an effect. So in this example, this is a distribution of the exponential mechanism, which is like nearly a delta
In
function.
this case, you're going to be releasing something from the data set.
No, you sample uniformly within the interval. You sample which interval with this exponential, but then within the interval, you sample uniformly. And this is what it looks like. So, this is the distribution of the median, the black line. You see it's not symmetric because it's what do I want to say? It's the median, it's not the mean. So we have different types of errors. But the distribution, actually more generally, distribution is just not very symmetric. This is the distribution of the empirical, of the sample error, the difference between what we release and the correct value. So when we add it, the effect is relatively negligible. So for a typical distribution, using the inverse sensitivity nearly has no effect on the accuracy of the mechanism. And again, depending on the epsilon, of course, but the effect is really minor, which is really cool in my opinion. So median is one of those extreme cases where if you try to take the first natural approach that you're like, oh, well, I have noise that scales with the sensitivity, that is the worst statistic you can imagine, has the worst sensitivity you can consider. And if you just think about it for another moment, you realize this is actually one of the easiest statistics to release. In a sense, for the same reason why originally you thought, oh, this is a robust statistic, it's going to be easy. Yes, it's robust. And we do take advantage of that property, but in the smart way. Okay, so that is the median.
By the way, would it make sense to theoretically, when you're doing the exponential mechanism, start with very, very large segments, and as you realize you're in smaller segments, just keep on applying
Segments of what?
Okay, we're sampling uniformly over the range, like we're separating segments, sampling over them, and then choosing one of them, right?
No. The segment I'm sampling exponentially by how many segments away it is from the correct one. Within the interval, I sample uniformly.
Yes. Would it make more sense to do the intervals, and if we see that we're in intervals, or we're a smaller number, like, okay, at this point, smaller numbers, we need to get more significant digits, we need to act maybe in smaller segments, and then doing it until we reach...
Wait, the size of the segment is determined by the data.
At that point, you're already getting some information by
No,
deciding.
but again, that's the thing. We are sampling from the exponential mechanism, which samples uniformly from all possible outputs, not uniformly, from all possible outputs, proportionally to e to the score. Okay? This turns out to be equivalent to sampling exponentially from the location, basically saying, how many steps away from the middle I would be. It decreases exponentially. It's actually an exponent that is weighted by the width. I'm somewhat simplifying, but give or take. Then once we chose an interval, we uniformly sample within that interval, and it just so happens to be equivalent to sampling from the exponential mechanism, and we know that the exponential mechanism is private, so we're good.
Okay. Yeah.
Okay, so we know how to sample privately from the median, but notice there's nothing here that was unique to the median. This algorithm works for any quantile. Because again, for any quantile, the sensitivity of the rate is still 1. The accuracy won't be as good because remember, as I mentioned, the accuracy is proportional in a way to the density around that point. Right? If changing one element there changes the value by much, then it's problematic. And typically, the density around the median is high. The density around the 99th percentile is lower, but still not negligible. So we can go back to. Okay, sorry. So this is the. Oh, okay. Sorry, I just want to show. So this is the distribution in terms of the natural units, the dollars, and this is the distribution in terms of the rank, the normalized rank. Okay, so basically you see the same story, but once in the old units and once in the new units. Now let's do the same thing for the mean estimation. So here's the algorithm. Estimate the two quantiles privately with the inverse sensitivity. Use it to truncate. This is what it looks like. So as you see, it is still somewhat biased because, again, the distribution is really asymmetric, so any truncation will be biased, but the effect of the bias is much smaller than the just sampling noise. So the distribution of the release of the error of the released value is getting relatively close to the underlying distribution. Still a small bias, but really not negligible. So we found a way to estimate the mean of a distribution where we know nearly nothing about the range. Like we used that 10 million, but as I said, now our sensitivity to the 10 million is logarithmic. I could change it to 100 million and the plot would look nearly identical. By first estimating privately the quantiles, truncating, then computing the mean, and of course, maybe I can push it a bit further. Like who said it needs to be the 1 and 99th quantile? Maybe it's the 5 and 95th. I don't know if I should split the epsilon budget in thirds. Maybe I should have like a different split. Whatever. If we have some distributional assumptions, we can analyze it and say, well, this is the accuracy guarantees in terms of the distributional assumptions, and therefore this is the best way to tune hyperparameters. If I don't have these assumptions, I need to do it heuristically or whatever. The important thing is just remember, this is the plot we have now, and this is the plot we had at our starting point. This is the difference that we get by, and now how many mechanisms we combine? 2. The Gaussian mechanism and the exponential mechanism. That's it. But the exponential mechanism was used in a very clever way. Okay, so I will not, the remaining part will be going a bit further, and we'll not cover all of it, but there are a few lessons that I want to take out of it. So say I know the mean, I know the median, in fact I know that I can know even a few quantiles. What's like one step above that I would like to know? A histogram. Right? Like, I don't want to have the whole data, but like, give me some sort of histogram. So, imagine I chose the width of a bin somehow. that will be a challenge that we'll cover in a moment, right? Because that itself might have some effect that you want to know from the data. But for simplicity, let's assume for a moment we already understood what the width of the bin should be. For example, we estimated 2 quantiles, I don't know, let's say the 48th and 52nd, and decide how the difference between the two will be the width of the bin, and something like that. And we created an histogram. So there's some number of elements in this bin and that bin, etc. And now I want to release it in a private manner. How can I do that?
You can put someone in every bin, that would be.
I can
You can put someone in every bin, that would
put
be
what in every bin?
noise.
I can add noise to every bin.
Just a number.
How much noise do I need to add? What is the sensitivity? So yes, adding noise to every bin.
One, because each bin can be changed by one person.
Good point. So every person can change only a single bin. So the sensitivity is 1. We're like in the rank case. But there are many bins. So now I need to pay composition over the number of bins. It's not fun. Do I?
One person can only change a single bin.
I don't know which bin will that person change, but I do know it will change only one. So adding noise that scales with, let's say, 1 over epsilon suffices. We don't care how big is the histogram. So here's a noisy histogram. I don't know if you remember the previous one. I mean, you can see that it's noisy because you see some of them have negative values, so clearly it's impossible. But of course, you can always do truncation or whatever. This is now post-processing, right? So with privacy, people don't care. You know that it's going to be a bit off, but really not by much. What kind of accuracy would we get? Well, the total number of elements and things like that, that might grow already, like the noise might grow like the square root of the number of bins, right? Because it's the sum of k. So if someone wants to know what the mean is, releasing a noisy histogram is a bad idea. But if someone wants to get a sense of the histogram, let's say sometimes people care about something called heavy hitters. In many cases, we have histograms where there are like a few bins with very large examples and all the rest are tiny. You want to know, what are the popular words that are now used in social network, things like that. So there are like a few hashtags that are dominating at every given moment. So a noisy histogram will do a great job for you. And what happens is the extent to which you can believe it is proportional to the number of examples in this bin. So the large bins are barely affected by privacy, and the tiny bins become unusable. And then utility-wise, they have the same problem. If your size of the width of the bin is too large, then yes, give or take how many elements were there, but you know that many people earn between $50,000 and $150,000 a year. Okay, that's not very helpful. If it's too small, then all of them will have a very low number. Then it's not very useful. Okay? So that is private histogram.
It's also useful for showing the median. It's like you can use the histogram to find a median. You said that's the root.
Yes, but again, the error will grow faster because you have about half of the bins on each side, and the noise was added to each one of them. So the number of elements on each side grows like the square root of the
The number
noise
of
times.
elements, of the number of elements.
No, the number of bins. So your accuracy degrades with the number of bins. The accuracy of the median.
And you do a process of shifting which bins you have.
Again, you can have a ton of tricks.
Yeah.
My point is, we need to realize that every way we release stuff has advantages and disadvantages from privacy, from utility. These are exactly the kind of things we need to consider. So I would just mention in words a very beautiful trick that is how we can estimate the Gaussian, the mean of a Gaussian, of a one-dimensional Gaussian distribution under no prior assumption, not even some logarithmic dependence on the range, but it works well only for the Gaussian. So when you think about it, in the case of the Gaussian distribution, we sort of know what is, let's go back. We know that in the case of the Gaussian distribution, clipping should be okay. If you clip like 5 standard deviations away or 6 standard deviations away from the mean, you're good. So the range doesn't matter, I only care about the standard deviation. But if I don't know the standard deviation, I don't know how wide should my truncation be, but more importantly, I don't know where should it be. Okay, let's say someone even gave me my standard deviation, I don't know where to locate that range. So here's an idea. Say I told you what the standard deviation was, but you have no assumption about where is the distribution located. How can you privately find that range? Once you found, that's easy. Then you truncate and you move on. So here's an insight. I just told you that the privacy doesn't degrade with the number of bins. At all. Not that it degrades slowly like logarithmically. It does not degrade at all. You can even consider infinitely many bins. That's also fine. So, you can, if you knew the right size of the bin, you could have just created an infinite histogram. And of course, values that are small enough, you truncate to 0, so you won't have, there are infinitely many problematic cases. And in one regime, you would have a peak. And that is where the mean is. So it has to be there, plus minus some number of standard deviations away. But to do that, you need to have the right width of the bin. Too wide, you still don't know where the mean is. Too narrow, and all bins will have very few examples. What is the right width of the bin in the case of the Gaussian mechanism? Or maybe I should ask, proportional to what value is the width of the bin, the optimal width of the bin?
The variance.
The standard deviation, the variance, right? Because if I take the width of the bin to be the standard deviation or 2 times or half, doesn't matter, then in the bin that contains the mean, we will have a constant probability, 5, 10, 20%, depending what is the factor you gave to the standard deviation. So we're going to have a significant amount of data there. So you can choose the width to be, let's say, one standard deviation, and then the mean is in one of them. Worst case, it's very, very close to the border, so you'll have 2 that are very prominent, but still, you won't have a big dilemma. You want to know where it is? Great. You found the range of the mean to within a standard deviation, then you add a few more to each side, you're good. But I don't know the standard deviation. How can I find the standard deviation? So then they came up, this is Salil Vadan and Kawa, I remember his first name. It's only in 2018, by the way. right? 12 years after differential privacy was defined, it was the first time we managed to find a way to estimate the mean of a one-dimensional Gaussian under no assumptions. And by the way, doing it for high-dimensional in a way that does not degrade with the dimension is not known until this day. Where the non-private version doesn't scale with the dimension, it scales with effective dimension. I mean, it does have to depend on the dimension, but if your distribution is very close to a lower dimension, then you scale with the effective dimension and not with the possible dimension, where privacy is not there yet. So just to give you a sense of still how far we are for solving basic stuff. So here's their proposal. So basically, if I know how to, if I know where, give or take, the mean is located, and I know the standard deviation, well, I would just truncate to within a constant number of standard deviations away. If I don't know where the mean is located, but I know the standard deviation, I'll do this histogram, I'll find where the mean is located. If I don't know the standard deviation, do the following thing. First of all, I can always transform any distribution to a Gaussian distribution with zero mean by just pairing pairs of elements and taking their difference. If for any Gaussian distribution, if I look at the distribution of the difference of pairs, then of course its expectation is zero and its variance is the same variance up to the factor 2. Okay, so so now I assume I have a zero mean distribution. And what they do is they do a histogram for the differences, for the distribution of the differences. Now, you might say, wait, but what is the width of that histogram? Here's the cool thing. So first of all, it's the absolute value, so they don't need to care about the zeros, the negative values. And the bins are not of the same width. They are logarithmically or exponentially. So basically, it's 1 to 2, 2 to 4, 4 to 8, and the same way 1 to half, half to quarter, etc. Right? Why is that? It's because once you get the estimation, you don't know that you have it to within a constant additive factor, but you know that you have it to within a constant multiplicative factor. And why is that important? Because the only thing we need the standard deviation for is just to know how much to truncate. So even if I truncate, and what's the width of the bin? So even if I chose the width of the bin to be twice as large, and even if I truncate it twice as much, it's okay, it's a constant factor. And in fact, reminding you of the coin press that I mentioned before, once we have give or take, we can do another round and then get a very good iteration. So this algorithm they just described, which is build a logarithmic histogram for the standard deviation estimated, then use that to create bins for the mean, find the mean, and then continue, is proven to work well for Gaussian. So I tried to implement it to this data set, and this is what I got. This is a distribution of the means with this sigma, which is not very useful. And in fact, even the sigma is not very useful. So this is the noise that happens. And why is that? The short version is we don't have a very well concentrated distribution. Remember, this is what it looked like. The whole point of, well, there's only one center, etc., breaks here. So it doesn't work. So I wanted to mention this technique because we went through the story of how can you sort of go back and forth between statistical assumptions and privacy guarantees in order to get more and more out of your data. But I wanted to show that some of these assumptions and some of these techniques only work for some types of data and not for others. So this very beautiful algorithm does not apply in this case. Okay, so just to recap, we spent full double lesson on just figuring out how I do this most basic task of estimating privately the mean and the median of like salary, not something really weird, in a somewhat reasonable way. And the answer that we found was median we managed to do quite well once we looked at it the right way, and mean not perfectly, but if you do the right tricks you can get to something relatively good, and if you don't it's really terrible, unless you have some prior knowledge. In the next weeks we'll try to do like some further steps, either ask some slightly more sophisticated questions like let's predict something from another thing, let's compute ratios, let's compute the mean on subsets, etc. How to use public information to maybe improve it, and we will also touch on a few more examples of the kind of ideas you were trying to raise throughout, which is let's create another step or identify another step that already exists that is privacy preserving for typical cases, and therefore we can maybe change it somehow that it will be privacy preserving for all cases, but will have only statistical effect or have minor statistical effects in typical cases, and therefore sort of we will keep everyone happy. So this is sort of the regime we will try to operate in the next few months. Thank you.